right, well, hello and good afternoon. Welcome to day 2 of Chem 400 lecture. Um, all right, here we go. Okay, so hey, how's it going? Day 2. We're about to wrap up week 1. Definitely exciting. I've got a couple things by way of announcements. Whoa, hang on. Let's normalize things here. There we go. Okay. All right, so just a couple things that I wanted to go over. So the first thing, and this should be highest priority on everybody's radar at this moment in time, the syllabus quiz. Is due tonight at 11 by 11:59. Failure to complete the syllabus quiz will result in you being dropped from the course. So if it is your intention to stay in the course, then you need to fill out the syllabus quiz and submit it to Canvas. Again, if you are enrolled, there is a portal for you to submit it to. Submit it in Canvas if you're enrolled in the class. If you're waitlisted, you email me. All right. The reason why we have this in place is for I want to know who is of the humans who are enrolled, who are actively participating and wanting to be in the course. Because someone who enrolled and maybe forgot or they're not really paying attention, those people need to get dropped and their place is given to a waitlisted student. We have a very dedicated and large population of waitlisted students at the moment, and we want to accommodate everyone who's putting an effort into the class. So again, if you're watching, if you're listening, this is due by 11:59 tonight, and if you miss it, if you are 1 minute late, you will be dropped. There is zero wiggle room for this assignment. Second piece of business, and this is for all of you waitlisters out there. After 11:59 tonight, we will know who did not fill out a syllabus quiz. We will be dropping all those students and giving those spots away to you, humans on the wait list. It's given in priority first. The only people on the wait list getting an ad code are people who have completed the syllabus quiz as well and turned it in. Excuse me, and then of those people who submitted it, they're given in priority of your spot on the wait list. So ad codes go out tomorrow. So keep an eye on your inbox. These will be delivered to your Los Rios email. So if you're not checking that, you'll miss it. The last day to add, I believe, is the 6th of September. Let me check. Yeah, September 6th is the last day to add to this class. If you get an ad code, immediately use it to enroll. All right. If you don't and you miss the deadline, you won't be able to take the class. So if you get your ad code, use it immediately. Use it the moment that it enters your inbox. Third, and when I say first batch of ad codes, waitlisted students, you've got 2 weeks to add, this week and next week. Over the weekend, the class will be taking the prereq exam, which usually there are students who don't do so well on it and end up dropping. So after the prereq exam closes, if people drop, there will be a second kind of wave of ad codes sent out. So if you don't get one in the first wave, hang on. All hope isn't lost. I believe the prereq exam closes on Wednesday of next week. So tomorrow, Thursday, first wave. After the prereq exam, if people drop, there will be another wave of ad codes sent out. So, but again, after that point, last day to add is the 6th. So then we'll be locked and loaded for the rest of the semester. So number 2 is for the waitlisted people. Number 3 is for everyone not waitlisted. I highly recommend that you start. I would start working on the lab exercise 1 if you haven't already. These I know that it's already up on my lab canvas page. I believe it's up on Dr. Gillies. I don't know if Dr. Chang is going to use them or not. So this at least applies to 75% of the class. These lab exercises are in Canvas. They're not timed. You can start them, stop them anytime you want. But they tend to be long. These are not written by me. These are written by FSC faculty, and they've been a part of the lab curriculum for as longer than I've been here. And so these kind of problem sets tend to be on the long side. I believe lab exercise 1 has like 57 questions on there. So if you start this thing an hour before it's due, you might not be able to finish it, depending upon how quickly you can work. But another good reason to start on this early is okay, awesome, cool. It looks like Dr. Gillies has that up on in her lab canvas sites as well. Another good reason to get a jump on this is lab exercise 1 is literally about sig figs, algebra, unit conversions, which are the 3 things on the prereq exam. So doing lab exercise 1 is studying for the prereq exam. If you're looking for kind of a way to like get going on that, this is a perfect thing. You kill 2 birds with 1 stone. You're getting an assignment done, and you are and you're studying for this weekend's exam all at once. 2 more pieces of information. Number 4, something that is in the syllabus. Those of you who have gone over the syllabus will have seen this, but I wanted to explicitly. Whoa, sorry. All of a sudden, it's really bugging me that my 4 is not lined up well with my 1. Let's fix that. One point that I wanted to state in lecture. It's in the syllabus. It's part of the course policy. But you should just all know up front, late assignments are not accepted. If you miss a submission deadline, then you've missed it. That ship has sailed. So you really need to be on top of things. Make sure you're looking at the lecture syllabus schedule, tentative lecture schedule, and then the lab schedule as well, so you don't miss any assignments. Finally, number 5, tonight in lab, I am going to start. It's going to be open office hours, but I'm going to begin with a just kind of like a mini lab lecture on significant figures, all right, or San Francisco's, depending upon how you interpret that abbreviation. So if you know you're rusty, or it's been a minute since you've done sig figs and you're like, you're looking for a place to start, maybe you don't get a lot out of reading, tune in tonight, 7. I'll be doing a mini lecture on sig figs, what they are, how to identify them, how to use them in calculations. And then on Monday of next week, I'll be doing a mini lecture on unit conversion. So if you're looking for a place to review for the final exam or the lab exercise, hit up office hours tonight. Also, one thing too, I've not yet gotten a chance to make it to my email today. I will be getting there sometime between lecture and lab. But if you've emailed me and you're like, why haven't I heard back? It's because I literally haven't opened my inbox yet. So Okay, let me see. We've got a bunch of comments. Let's see. Amanda. Okay, great question about the edition. So you can use any edition of the textbook. All of the content is the same. The only thing that's different is the only thing different about the editions is that the problem homework problem numbers are different. I assign practice homework. It's not graded. You don't have to turn it in. It's just there for your edification. Out of the second and third editions, because the older editions tend to be cheaper. But if you can only find a fourth or fifth, you can totally use it. They're totally fine. Again, I put out stuff for the older editions because usually you can find them for like $20 or so. Let's see. Yeah, check out Amazon. Let's see. Oh, weird. Okay, so Afon. Often, I would ask her. So it looks like Dr. Chang has the lab exercise up, but there's a 30-minute time limit, which is probably there by accident. So I would ask her about it, see if she's gonna change it, because I feel like it's too long to do in 30 minutes. But if she feels that that's what's fair, she's the professor of her course. But my guess is she probably doesn't even realize it. So I would ask her about that. Oh gosh, Eric. You do yeah. Eric, totally don't buy both textbooks. There'd be no reason to. I have two editions out there because those are two older editions that a lot of people have, but or are easy to find. But yeah, there's no reason to have both. When will the homework be posted on Canvas? As soon as I get it finished. Is the honest answer. And if you're worried about like the deadlines because you're like, I want to start this now, and homework for chapter 2 isn't available. If I'm late getting them up, I'll also adjust the due date till later. So you don't need to worry about me putting you in a time bind, Sammy. So okay, thank you, everyone, for all the questions. Let's go ahead and dive into some science, not some new science, some science for the first time in our time together. This may seem, hopefully this will be a bit of review. It may seem familiar. I'm just going to go over some stuff just to make sure we're all on the same page, and then we'll start pushing the boundaries. But here at the beginning, it should feel mostly like a review of Chem 305. All right. So, we're just going to start very, very, very fundamental here. We're going to talk about elements, all right? And so this is the periodic table of elements. And each element has its own slot on the periodic table. And each element has its own symbol, etc. And the periodic table is packed full of information. I'm sure as you recall, maybe vaguely, maybe distinctly from your prerequisite course, we can do a lot of things. We can use this for a lot of different things. This is a tool. This is our Swiss Army knife of the course. And I'd like to begin by talking about everyone's favorite element, silicon. So on the periodic table, every element has its own discrete little cell, all right? And this right here is called the elemental symbol. The elemental symbols are either one letter or two letters, a capital letter and a lowercase letter. This is to differentiate elements that start with the same letter. So, for example, if you compare silicon to sulfur or selenium, right? All of these start with S. Sulfur got the single S, so silicon and selenium each get an additional letter. Now, above the element on the periodic table is a number, and this right here is called the atomic number. All right, the atomic number takes a symbol of a capital Z, all right? And Z, that atomic number, equals the number of protons in that nucleus, all right? The number of protons in that element's nucleus, all right? Now, for a neutral, elements are all neutral, which means that they are not charged at all. So, for a neutral element, this is worth noting. If you have a neutral element, so not an ion, the number of protons, neutral means that there's no charge. That means the number of negatives and positives are the same. So for a neutral element, the number of protons is equal to the number of electrons. All right, so technically the atomic number just tells you the number of protons, but if we're dealing with a neutral element, you also know that that is the number of electrons. So silicon, a silicon atom, has 14 protons, 14 electrons. All right, the last piece of information that we're going to talk about right now is beneath the elemental symbol. There is another number for silicon. That number is 28.09, and this number right here is called the atomic mass. All right, it is the often you'll hear people, me included, call this the atomic weight. And for those of you who come from a more pristine physics background, you might say like, well, weight and mass are different. And I want you to know that I know that and agree with you. I just don't care. Because weight and mass are related by a scalar constant number. So we tend to use them interchangeably, and I use them interchangeably. So just to let everyone know, I will also call this the atomic weight, atomic mass, atomic weight. I flip back and forth, and they mean the same thing for our purposes here. In a physics class, they might splice hairs, but you know, we're chemists. We're a little more blue collar. So that is the atomic mass. The units are not given explicitly in the periodic table, but the unit for atomic mass is AMU. All right, and that stands for atomic mass unit. So one atom of silicon has a mass of 28.09 AMU, atomic mass units. All right, now, let's see. Okay, so we've got the atomic number, the atomic mass, and the elemental symbol. I want to make one comment about the elemental symbol. Before moving on. So, the elemental symbol, to be technically correct, to be technically correct, the elemental symbol is an uppercase followed by a lowercase, all right? So this is upper, the first letter is uppercase. The second letter is lowercase. All right. Now, when it comes, so that is technically correct. If you use an uppercase for the second letter in the atomic elemental symbol, it's technically wrong. That being said, if you look at iridium, you'll totally see me write iridium as IR. Technically, that R is uppercase. It's just smaller. And I'm totally fine if you do this. The one thing you got to be careful is for that second letter, you got to make sure when you're writing it that this thing is small. All right? The reason is there are elements out there like cesium, who is C, elemental symbol is CS. And if you write these the same size, oops. If you were writing cesium but you wrote CS, this is carbon followed by sulfur. All right? So you just got to make sure that that second letter is small, not large. All right? I don't care if you write it as a small uppercase or small lowercase, but it's got to be small. If you write it full size, that's something where you might find yourself losing points because it can change the meaning. It can change a cesium atom to a carbon and a sulfur atom if you're not careful. Hopefully that makes sense. Okay, let me see. We've got a couple. Will I require you to use AMU in your homework? Paul, I'm not sure I totally understand the question, but I think the answer depends upon the question. If I ask you to, how many, okay, let me know if this answers your question. In this class, and this is something that's just good to know. Every correct answer has three things. There's a super specific scientific word, right? Every correct answer has three things. It must have the correct value, right? So your number has to be correct. It must have the correct sig figs, all right, the correct number of sig figs. And finally, it must have the correct units. Every correct answer has these three things. Any answer that's missing one or more will be incorrect. And so I guess this is how I'm trying to answer the problem. Let me know if this is what you're asking. But if you're solving a problem where it says calculate the molecular weight of a given molecule in AMU, you'll have to include units as part of the correct answer. But again, I'm not sure if I've totally understood the question. Karen, that is a great question. So Karen asked, is the atomic number, are the atomic number and the mass number the same thing? Oh, sorry, not atomic number. Are the atomic mass and mass number the same? And these two are not. The atomic mass is not the mass number. Okay, Paul. Or, sorry, not Paul. Sorry, Paul V. Totally. And I apologize for messing up your name. I'm going to work hard on learning everybody's over the course of this semester. Karen, the atomic mass is different than the mass number, and we'll be talking about the mass number actually coming up on this very next slide. So let's dig into that. Now, so we've talked about elements, all right? Now, an element, what defines an element is the proton count, right? Is the atomic number. Everything, any atom with 14 electrons is a silicon atom. Any atom with, sorry, I said electrons, with 14 protons is a silicon atom. Any atom with 6 protons is a carbon atom. If you add 1 proton to carbon and now it has 7, it's no longer carbon, it's nitrogen. So the element's identity is tied to the proton count. The proton count determines an element's identity. However, we know that there are protons, there are electrons, and there are neutrons, right? There are 3 subatomic particles, and the number of neutrons can vary within a given element, all right? And that leads us to a discussion of isotopes. 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 All right, isotopes are atoms of the same element with varying proton counts. All right, elements, atoms of the same element with varying proton counts. All right, sorry, holy moly, that is like the completely wrong thing, right? You can't have different proton counts if you're of the same element. Varying neutron counts. Let's try that on for size. Richard, that is a great question. If the atom is neutral, the electron count equals the proton count. If not, there are ways of using the periodic table, but that's a little bit ahead of where we are now. So we'll get there, but one step at a time. Now, isotopes are atoms of the same element with varying neutron counts. All right. Now you may be wondering, how do you know how many neutrons a particular atom has? And the neutron count of an atom, of an element, is nowhere on the periodic table. All right, because they vary too much. There's no way of including this information in a systematic way. So you will not find your neutron count on the periodic table. You need an additional piece of information, and that additional piece of information, Karen, this will tie into your question, is the mass number. All right, so the mass number which is abbreviated with a capital A. The mass number is equal to the number of protons in the nucleus plus the number of neutrons. So these two together, all right? And remember that the number of protons is equal to the atomic number, Z, all right? And with the mass number and the atomic number, we can start writing elements using what's called isotopic nomenclature. It's a way to specify what isotope of an atom you're talking about, all right? So you'll see this written like so, the elemental symbol with the mass number superscripted and the atomic number subscripted, or you'll see an elemental symbol written with a dash followed by the mass number, or sometimes the element's name will be written out, followed by a dash and the mass number. All right, so these are the three formats you see isotopes written in. So this is kind of abstract, kind of, well, abstract. Let's actually sink our teeth into it. So, for example, you could have an isotope of hydrogen known as deuterium like this. All right. If you ran into this is an isotopic nomenclature. This 2 up here, this is the mass number, right? So that means, and then this 1 down here is the atomic number. So that tells us Z equals 1 means that we have 1 proton in this isotope, and A equals 2 means that our protons plus our neutrons equal 2. But guess what? We know our proton count is 1, so 1 plus our number of neutrons equals 2. That means that there is 1 neutron in this isotope. All right? You could run into, for example, it's not the only isotopic, the only way to write out a specific isotope. So you could run into nitrogen 14, all right? And again, this right here is the mass number, all right? Now you may be looking at this, and if I asked you how many protons, how many neutrons are in this isotope, you may be going, well, I only know A. I only know that 14 is equal to my protons, number of protons plus the number of neutrons. And that is correct. But you know something else. You know that you're dealing with nitrogen, which means you can find it on the periodic table. And by locating nitrogen on the periodic table, that tells you that Z, the atomic number, is 7. So we're dealing with 7 protons. Now you can use the mass number. 14 is equal to 7 plus the number of neutrons. And you do a little algebra to realize that nitrogen 14 has 7 neutrons. Right? The number of neutrons is equal to 7. So that's how you can kind of use these two formats in tandem. You don't have to explicitly be told the atomic number because you can always look that up on the periodic table. The mass number you have to be given. You won't find that anywhere on the periodic table. All right, now the number of different isotopes that can be found for any particular element in nature varies. Some elements have a lot of different stable isotopes. Some have just a few. All right. Carbon has 3 naturally occurring isotopes. It has carbon 12, excuse me, carbon 13, and carbon 14. All right. There's 3 naturally occurring isotopes. If I were to ask you to figure out how many protons and neutrons are present in each atom of carbon, well, in each isotope of carbon, I should say, because these are all carbons, they will all have the same proton count. There's 6 protons in every atom of carbon, and that is always true because your proton count defines your element's identity. And then we've got the mass number up here, right, for each one. So we just subtract our proton count from the mass number to figure out how many neutrons. So carbon-12 has 6 protons and 6 neutrons. Carbon-13, 6 protons and 7 neutrons. Carbon-14, 6 protons, followed by 8 neutrons. Now, because these 3 isotopes have different number of particles in their nucleus, they all have different masses. This should come as no surprise. Carbon-12 has a mass of 12.0000 AMU, one isotope of carbon-12. Carbon-13 has an atomic mass of 13.0034 AMU, and carbon-14 has a mass of 14.0032 atomic mass units. All right. Now, you might be going, wait a minute. On the periodic table, there aren't 3 masses of carbon. There's only 1 mass, right? How is it that we have 3 different atomic masses, but there's only 1 reported on the periodic table? And a simple solution to this you might be thinking, well, maybe the mass on the periodic table is an average, right? Maybe because there's 3 isotopes, it makes sense that the mass that's reported is an average of all these 3. Well, that answer is not wrong, but it's also not 100% correct. There's an added detail. If you took the average of 12, 13, and 14, these 3 masses average out to approximately 13 AMU. All right, not applying any rules for sig figs or anything, but if you took the average, it'd come out to be about 13, a little bit more. But if you look at the periodic table, carbon, atomic number of 6. Carbon has an atomic mass of 12.01 AMU. Decidedly not the average of these 3 masses. So what's going on here? Why is it almost just the mass of carbon-12 when there's 2 other isotopes that weigh so much more? And the answer has to do with something called natural abundance. All right, there are 3 naturally occurring isotopes of carbon in nature, but 98.93% of every carbon atom found in nature is carbon-12. All right, 1.07% is carbon-13, and 1 times 10 to the negative 10th percent is carbon-14. So the number reported on the periodic table for every element is not a pure average, right? There's an assumption that goes in with taking an average, and that assumption is that every number that you're taking the average of has an equal representation. But as you can see, carbon-14 and carbon-13 are in the severe minority. What goes into the calculation for the atomic mass that we see on the periodic table is something called a weighted average. All right, this is a weighted average, and we need to take into account the natural abundance of each isotope in addition to its mass in order to calculate the atomic mass. Aston, that is an excellent question. Aston's question is, where does the 0.0034 AMU of mass come from in carbon-13? So it turns out that a neutron does not its mass is close to 1 AMU, but it's not exactly 1 AMU. So that's why you end up with these kind of weird decimals as you add more and more subatomic particles. Now, you may even notice that you're like, well, okay, so I could accept maybe that a neutron has a mass of 1.0034, but why is the next one, we've added 2 neutrons, why is it 0.0032? Shouldn't it be 0.0068? And that is another detail that's covered, I think maybe in chapter 14, when it comes to the binding energy. So when you have subatomic particles coming together to form a nuclei, some of their mass is converted into energy that holds those nucleons together in the nuclei. So it's not even, as you're adding neutrons for new isotopes, it's not even like a clean mass unit of 1.00 something plus another 1.00 something, because with each particle that you're adding to the nucleus, some of that mass is being converted into energy, to the binding energy to hold that nucleus together. So it's around 1 proton, 1 neutron adding is around 1 AMU, but it's not a perfect clean AMU. So that is the long-winded answer to your question. You will not be tested on that information that I just stated, and the mass of each isotope will always be provided. So you don't have to memorize these. You don't have to worry about finding them, looking them up. They'll be provided for you in the problem. All right. So let's talk about... You are welcome, Aston. That is an excellent observation and a fantastic question. So I want to talk for a minute about how to take a weighted average. All right. For a weighted average, you take the mass of each isotope. So for example, the mass of isotope 1 in AMU times its percentage over 100, right? Because you gotta convert that percentage to a decimal. You take each isotope, multiply it by its percent abundance over 100. And this will change. Some isotopes, there's only, for some elements, there's only 2 naturally occurring isotopes. Some have 3, some have more. But however many you have, you multiply each one by its percent abundance over 100. And then you take the sum, and the answer that sum is the weighted average all right, and that weighted average will be the atomic mass that you see on the periodic table. I don't normally do this, but this early in the semester, it's kind of a tradition for me. I don't always say explicitly like, oh, you will see a problem like this on the exam, but I do hear and when I say the exam, not the prereq exam. This is an excellent exam 1 problem right here. It always calculating an atomic mass using a weighted average always makes it onto the exams I write. So this is one of those things that you want to learn because you will definitely be tested on it. So keeping that in mind, as we move forward, let's calculate the atomic mass for carbon. Using these 3 isotopes and the given natural abundance. So let's calculate carbon's atomic mass. All right, so what we got to do is we need to take each atomic mass, or the atomic mass of each isotope, and multiply it by the natural abundance, right, which is given as a percentage, and we need to convert that natural abundance into a decimal. So by dividing, you divide by 100. So we have 12.0000 AMU times 98.3 over 100. Then we have 13.0034 AMU times 1.07 over 100. Then we have 14.0032 atomic mass units times its percent abundance, which is 1 times 10 to the negative 10 over 100. All right. Let's see. I'm going to lasso tool this guy down. This is one of the nice things about teaching online. I do not have a lasso tool on my whiteboard in class. All right. So let's see. Hey, check this out. I am busting out my calculator for the first time this semester. It will not be the last time. All right. So let's take these. Now, I'm going to be applying the rules for sig figs as I go, because like I said, this is one of those things that I'm just assuming that you know. If you find yourself a little bit lost here, here's a little commercial for office hours tonight. Drop by office hours. We'll be going over this in detail. Now, we're doing a multiplication here, so 12.0000 times 98.93 divided by 100. All right, this comes out to be 11.8716. All right, that's the value that my calculator is giving me. I know that the units here are AMU. As far as sig figs go, this was a multiplication, so I can only keep the fewest number of sig figs. All right, and 98.93 has 4. 12.0000 has 6. So I can only keep 4. So I'm going to put lines 1, 2, 3, 4. I'm going to wait to round to the end. The correct way to do sig figs is you wait to round to the end, but you apply the rules as you go. So I'm just going to leave this 11.8716 as is, but you can see I put these lines under here to remind myself that that value has only one sig fig. Bailey, great question. I will always give you the percent abundances in the problem, so you never have to worry about even like having to look them up in the book. If you're on an exam, you're working this problem on exam 1, not the prereq exam, I will give you them in the problem, so you don't have to waste time looking them up. All right, excellent question. So that's our first. Next, we have 13.0034 times 1.07. Oh, hang on. 1.07 divided by 100. All right. The value that I'm getting here is 0.13913638 AMU. Sig figs wise, my atomic mass has 1, 2, 3, 4, 5, 6 sig figs, but my natural abundance only has 3, so I can only keep 3. Gianna, great question. Every non-zero digit is significant. 0 sometimes is significant, sometimes it's not. There are 2 instances where 0 is significant, and I'll be going over those tonight in office hours. So you can catch the review tonight, because sometimes it is, sometimes it isn't. You got to figure it out. All right, for the last one, we have 14.0032 times 1 over 10 to the negative 10 divided by 100. This comes out to be 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 zeros. 11 zeros followed by a 1, 4, 0, 0, 3, 2 AMU. All right. Our atomic mass has 6 sig figs. Our percent abundance only has 1, so we can only keep 1 significant digit here. All right. Now it's time to add these all together. All right, we're adding these all together. And when we do, let's see. So 11.8716 plus 0.13913638 plus the rest of it. So our value comes out to be 12.010736. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 1, 4, 0, 0, 3, 2 AMU. All right, that is our value. Now we have to apply the rules for sig figs. Then we have to apply the rules for sig figs for addition, which are different than multiplication and division. When you're dealing with addition, you have to go with the least precise number. And our least precise number is that 11.87. Its last significant digit is in the second decimal place. So you have to round your entire number to the second decimal place. So our correct answer with the correct value, sig figs, and units is 12.01 AMU. All right, that is our correct answer. So, again, we use the rules for multiplication and the rules for addition sequentially. If you're able to follow, awesome. You are most likely ready to take the prereq exam. If that terrified you, or if you have no idea what's going on, tune in to office hours, or if you don't want to tune in at 7, watch it later. I will be going over the rules for sig figs explicitly, so you will know how to deal after watching. All right. Any questions on that business before we move on? All right. Okay. Just no questions. Just dead silence in the comment feed, in the live chat. Okay. So we've got a couple other things that we want to talk about. I want to kind of do a little bit of an intro to the periodic table. Oh, let's see. "17 Mayhem." That is correct. All right. So let's talk for a minute about the periodic table. I said earlier that this is kind of our Swiss Army knife of the course. We are going to use this so many times in so many ways. But I wanted to do a little review of just some things that, again, you should have learned these in your prerequisite course, but I just want to make sure that we're all on the same page here. There's several different ways to slice the periodic table up, all right? And the first division is kind of the division between metals and non-metals, all right? And that, some periodic tables include this, some do not, but But the division between metals and nonmetals are right here. It starts under boron, between boron and aluminum, and it stair steps down. All right? So this is kind of the railroad track that divides the metals and the nonmetals on the periodic table. All right? And you will find that your nonmetals are all over here. Whoa. And right there. All right, these are our nonmetals, and then our metals you can find on the other side of this railroad track. And down here as well. All right, so these are our metals, and in green, these are our non-metals. All the non-metals are to the right of that kind of dividing line. The metals are to the left, with the notable exception of hydrogen. Hopefully that does not come as a surprise to you that hydrogen gas is a non-metal. But we just have to explicitly point that out. So you can divide the periodic table into metals and non-metals. There's a interesting little pocket right here at the intersection between your metals and your non-metals, all right? Because the thing is, the category metal and non-metal is based on observation, based on shared properties, but it's not a light switch. It's not something that goes on and off. And it turns out that, well, let's see, I'm going to go a little darker here. It turns out that the elements that are kind of touching this line between metals and nonmetals, these guys are known as metalloids. These things right in here. Well, that just blanked everything out. So these are known as metalloids because they have some metallic characteristics and some non-metallic characteristics. These are where you find, for example, our semiconductors. We know that non-metals are insulators. They do not conduct electricity. Metals are conductive. They conduct electricity. And your semiconductors, which all of our computer processors are based on, are all found in the metalloids. They kind of have some metallic properties, some non-metallic properties. They're the weird tweener kids who kind of bridge the gap between the metalheads over here and the kind of like hippie acoustic folk people. I don't know why I did a rock-on symbol for them. I don't know. Hippie acoustics, non-metal, metals, hardcore. You got these kind of weird indie rock punk kids who have some kind of folksy properties and then a little bit of a harder edge too. It's a way to divide the periodic table up. Let's see. Shoot, I guess that brings us right up to 2 o'clock. So I think this is where I'm going to hit pause. There are more ways, different ways to chop up the periodic table. We'll talk about that in class on Monday, but for now, we're going to pause it here. Tune in tonight or watch at your own convenience for a sig fig review, what they are, how to identify them, how to use them in calculations. And of course, if you are planning on staying enrolled in the class, submit your syllabus quiz because when I wake up tomorrow morning, every late submission and every lack of a submission, you guys will all get dropped. And waitlist humans, keep your eye on the on your Los Rios inbox, because that is where your ad code will be coming. Also, you will only get an ad code directly from me if you're in my lab section. So if you're in Dr. Chang's waitlist, you'll get an email from her. If you're on Dr. Gilly's waitlist, you'll get an email from her. So it may not be coming explicitly from me. So if you check your inbox and you're like, I didn't see any email from you. Did I add or did I not add? It'll be coming from whoever's from your lab instructor, whoever that may be. Cool. All right, last question. Confused on what to buy. The kids do rock. Alrighty. Okay, cool. So, thanks everyone for dropping in. It's been an awesome first week. It'll be an awesome second week. We're just going to keep rolling with the awesome. I might see some of you guys later in office hours tonight. But if I don't, I'll catch you Monday morning. All right? Later.